Okay, welcome to video 5, which will be the fastest video probably I will ever do for you for the remainder of the school year. Let me go ahead and share the screen. And just like I stated in the previous videos, if I move through quickly on a topic and you feel like maybe because you weren't in honors or maybe you're a current senior and it's been a long time since you've had that topic, there are slides that are under Unit 1 and there are things in here, obviously, that you can keep practicing to try to brush up on some skills. There's also, channels on YouTube where you can watch videos. You can just put in the topic. You can even put in AP Chemistry 1.4, 1.3. Actually, you probably should just say AP Chemistry like Unit 1. Sorry. Most people are not going to do like 1.4, 1.5 like I am. But you could put in AP Chemistry Unit 1 and find lots of videos. So today is all about electron configuration, and that is something that you are supposed to remember from a previous chemistry class. So we know that in the nucleus of an atom are the protons and the neutrons, and in these shells, or what really are called energy levels, are electrons. Remember, in 8th grade, you probably talked about this model of the atom, which is called the Niels Bohr model of the atom. And those rings or shells are where the electrons live. And like this right here would be the nucleus, that center part. And remember, that's not really what it looks like. We talked about in 10th grade how there are these orbitals called s orbitals or p orbitals, and like p orbitals are dumbbell shaped. And there's all these places that electrons live that are very different from that model. So just to kind of review this, if you look at like the periodic table and you look at copper, if I ask you how many protons, neutrons, and electrons copper has, well, the protons are its atomic number. So it has 29 protons. Now, all atoms that are just chilling out on the periodic table are neutral. So that means it also has 29 electrons. If you're going to tell me how many neutrons, which is the mass, protons plus neutrons are the mass, you have to know which isotope, okay? Now, this is the average atomic mass that is reported on the periodic table. Not all elements have an isotope, okay, or have isotopes, I should say. Some of them only come one way. Where, like you wouldn't have like copper 12, copper 13. And like no one has memorized which atoms have isotopes. Like if you said to me, hey, how many isotopes does selenium have? I would be like, I don't know. Does it have any isotopes? I'd have to Google that information. Just because you see a decimal here for an average atomic mass does not mean that there were more than one isotopes for that atom. The reason that there are decimals really truly is because remember I told you these numbers are reported in AMUs, or atomic mass units. And I told you that every proton and neutron is not really just one. We say that every proton and neutron have like a mass of 1, but we're rounding that to a whole number 1. It's not really a whole number. So you would take the mass that's on the periodic table normally, and you would say, okay, whatever that number is minus the number of protons, that would be the number of neutrons. Because remember, I'm telling you, the mass on the periodic table is protons plus neutrons. And we're saying that every proton has a mass of 1 and every neutron has a mass of 1. Of course, like I said, it's really 1.0 something, something, something. But the only way you could tell me how many neutrons copper has is you would have to know the actual mass. It would have to be some kind of rounded whole number. And so you'd have to know, are there any isotopes? Okay, so I'm going to go ahead and give you that information. Copper comes as 63 and copper comes as 65. It does have 2 isotopes. And this number right here tells you the 63 isotope must be more abundant because the average is closer to 63. So copper with a 63 mass would have 34 neutrons. Where am I getting that? 63 minus 29. And copper that is a mass of 65 would have 36 neutrons. Okay, so I'm just, again, keeping up with the idea of protons plus neutrons equals mass. Now, in case you haven't noticed, I'm not heavily reviewing things from 10th grade. You are supposed to be coming in with some incoming information. So if you're like, I have no idea what's happening, you're going to have to kind of catch up on this. If you need me to send you anything, like any honors notes, I can do that. So when copper, which is a metal, reacts with a non-metal, that would be an ionic bond, which means it would form a charge or an ion, meaning it would give away electrons if it's a metal or gain electrons if it's a non-metal. So it's saying, hey, often copper becomes copper with a +1 charge. What does that mean? It means he gave away 1 electron. So he would still have 29 protons. The protons don't change just because you bond with somebody, but now he would have 28 electrons. Why? He gave 1 away to take a 1+ charge, and whatever his neutron number would be, it would be the same. You don't move around neutrons. Electron configurations are shown here. These are electron configurations of boron, carbon, and nitrogen, and these are what are called electron orbital diagrams. We did these last year. Remember, there's a couple of rules. You cannot have 2 arrows of the same spin. They must be up, down. I will say I don't like this diagram, how it shows down first. It's usually always written up, down. Okay. Even though I can edit this worksheet, I can't really change those arrows. It's like a graphic, and I didn't want to do that. But just know we normally are going to write up, down. Are you going to probably be drawing orbital diagrams on the AP exam? Probably not. Another rule was that, you remember, everybody has to take their own bus seat before you double up. Okay, that was Hund's rule. Y'all used to call it the bus seat rule. And then you do remember that all S's hold 2 electrons. Each P can hold a total of 6 electrons. There's like an orbital within, there's 3 orbitals within each P sublevel. And so you've got the opportunity, if these P's were full, to hold a total of 6 electrons. So as you can see here, these P's are not full. Now, inner electrons are called core electrons, and outer electrons are called valence electrons. The only thing that might be new to you about that is the word core. Again, you can see here, like P's are dumbbell shaped, D's are like 4-leaf clover shape. There's a shape to these electron clouds where electrons live. And so you're not going to have to like know the shapes, but it's helpful for you to see that. There are orbitals that are called F orbitals. The F orbitals are the bottom of the periodic table. So these are where your F orbitals would be, and these lanthanides and actinides, these bright purple fuchsia things down here at the bottom, you can see there's a 4F and a 5F. Each F orbital can hold a total of 14 electrons. Each D orbital can hold a total of 10. Each P, like I said, can hold 6. What am I even talking about? I'm counting squares. The way I know a P can hold a 6 is look over here on this P block. 1, 2, 3, 4, 5, 6. There's 6 squares. How would I know that the D blocks can hold 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Each S holds 2. 1, 2. Okay. Remember, you're counting squares. Hopefully this is bringing back some memories to you. You do need to realize that these energy levels or periods are where you're getting that first number. Like if you say 1s2, 2s2, the 2 in front of the S tells you you're in the second row. Okay, this is heavy, heavy, heavy on review. So the first shell, or the first energy level, meaning the first row, is small and can only hold 1 s orbital, or a total of 2 electrons. The second row or shell is bigger, and you can now hold an s orbital, and you can have a p orbital. And remember that p is going to have like 3 blanks, so 3 p's. So you can hold a total of 8 electrons here. The S is going to hold 2, and the P can hold 6. Okay. And then once you get to that third row or shell, that is where you can now have an S, a P, and a D. What's the trick to that? Okay. The trick to that is to remember, when you're looking at that third row, okay, you only see the S and the P. Okay. What do I mean by you don't see the D? Okay. Remind you, remember, this is 3D. When you get into that fourth row, the filling order is 4s, then you have to fill 3D, which is over here from scandium to zinc, and then this becomes where you start saying 4p. The D block, or the D, drops back an energy level. Okay, it's just the way that the clouds and the orbitals are inside of an atom. Also, it's the number one missed thing. There's probably going to be an electron configuration in May as an FRQ. I think there wasn't last year, which was crazy. They were like, you said there was going to be one. There almost always is one. But it's usually going to be something that involves you remembering that when you get to a D, you're in the fourth row, and it is 3D. It goes back at energy level. If you're ever asked about Fs, which you would not be asked about them on the AP exam, they go back 2 energy levels. So it goes 6s, and then you would do 5D, okay? But then if you are looking at the fact, like, so this comes from that, if you remember when you did your little coloring periodic table. The lanthanides, La, they're this first row down here at the bottom in this hot pink. So you're actually going to say that you're going to go, you're going to be in 6s. So you're going to say 6s, and then you're going to say 5D, and then 4F. Okay, so the F's go back 2 numbers. We don't do F block filling. It can get pretty confusing. Does it matter if you put like the F in front of the D or the D in front of the F? Not really, as long as you've got this number that is correct. Like you went back 2 for the F and back 1 for the D. I'm not going to go too far into that because it's not on the AP exam. Now, I've mentioned the rules. One rule was, again, that you have to have opposite spin electrons. That's Pauli. Another rule was the bus seat rule. Everybody gets a seat before you double somebody up. Aufbau rule basically says you must fill in order. You can't skip. Okay, now you could skip if you're exciting an electron, but we're not going to be doing exciting electrons when we are asked for an electron configuration usually, because they're going to say, give us the ground state. A ground state electron configuration means that you're grounded, like you're not excited. Okay, so let's just keep going because it's better taught practicing. So it's like, hey, let's look at the electron configuration for fluorine. So you find fluorine. He has 9 electrons. He also has 9 protons. Remember, everybody's got the same number of protons and electrons. So you know that because he has 9, your exponents must add to be 9. Those little exponents tell you the number of electrons. But you're just going to fill in order, okay? You're going to go, okay, 1s2, 1s2. Remember, helium is still the 1s. 2s2, 3p, 1, 2, 3, 4, 5. And then stop at fluorine, 3p5. Okay? I'm sorry, I said 3p, 2p. I'm still in the second row, 2p5. 3p was wrong, sorry. So let's look at iron. Okay, well, first you find iron and you see how many electrons he had. Here he is. He has 26 electrons. And then you just start filling. Okay, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. I'm right here now at calcium. 1, 2, 3, 4, 5, 6. 3d6. That's iron. Okay. All right, look at scandium. Okay, here is the configuration for scandium, and it says, hey, what if I ask you for the noble gas shorthand? Well, everybody likes those. You find scandium, you go backwards until you get to the noble gas that comes just before him, and you put that in brackets. So that would be argon. And then you just finish writing out the rest that comes after argon. 4s2, 3d, 1. Now, I will tell you, all noble gases end in a P6. So if you're like, oh, I can't figure out what I write after I write the argon in brackets, you just go up here and write whatever comes after the P6. Now, let's look here. This says, well, what about for arsenic? Well, first of all, you gotta know that arsenic is AS, but it's okay if you didn't. I feel like by the end of the year you would, but you're going to find him. Okay, so he is right here. He's number 33. So we're going to have 33 electrons. The standard configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Remember, there's 10 blocks on the D block. And then I'm going to go over into 4p and 4p, 1, 2, 3. What if I need the double gas? Well, I'm going to have to go back to argon. Argon in brackets. Remember, I write everything after that full P6. And finish it out. Okay, now it says, what if you have calcium 2+? What does that 2+ mean? It means he lost 2 electrons. Okay, so what would he be as his electron configuration? Well, go back and find him. He had 20 electrons. He had 20 protons and he had 20 electrons, but he lost 2. So now he has 18 electrons. What does that make him like? He's like argon. Okay, we would say he is isoelectronic. Iso means same, or that he has the same electron configuration as argon. Okay, well, that means he's like a noble gas. Okay, well, isn't that everybody's goal? Doesn't everybody want to be like a noble gas? That's why calcium takes a 2+ charge, so he can have that full outer shell or full outer valence shell of 8 electrons. So you're going to just write 1s2, 2s2, 2p6, 3s2, 3p6. You're going to finish right here on the 3rd row at p6 with argon, 18 electrons. Now, let's come up here and do an orbital diagram of one of these. Let's do iron, okay? 1s, 2s, 2p. Remember, there's 3. 3s. Okay, I'm going to come out here and finish. 3p, 3 houses for that. 4s. And for 3d, there's 5 orbitals. How did I know that? It can hold 10, and each little spot can hold 2. 5 times 2 is 10. So this is 3d. Okay, look back at the notes about this. It talks about how D's can hold 10 and that there will be 5 spots. So then I'm going to do my arrows. Up, down, up, down, up, 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 bus C, down, down, down. How do I know? It's 2p6. Up, down, up, 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 down, down, down. 4s2, up, down. Now I'm going to come over here. 3d held 6. 1, 2, 3, 4, 5, 6. There's 4 unpaired electrons. Unpaired electrons are active. That is why iron is very magnetic, okay? You'll hear talk of unpaired electrons and how that makes things magnetic. What is common is students would do this. 1, 2, 3, 4, 5, 6, and that is wrong. That's not following Hund's rule, which is everybody gets a bus seat before you double somebody up. Okay, those are some messy arrows, but you get it. You'll probably hear talk of like the word paramagnetic and diamagnetic. If you take college chemistry, hold on, I'm looking something up really quick to try to get a good definition of that. Let's see. It's not something I ask you about on AP, but sometimes I'll throw things in that would not even be asked about. 2 types of magnetism based on electron spin and motion. You could be diamagnetic, paramagnetic, or ferromagnetic. Let's see. There's other types too. Paramagnetic. In a diamagnetic atom, all of the shells will be complete. In a paramagnetic atom, subshells are incompletely filled with electrons. So paramagnetic would be the word that we would use for iron because it would have those unpaired electrons in that d orbital. Now, let's talk about this again. This is the, like you would call the energy level. And then, excuse me, and then these would be the orbitals. I didn't mean to get rid of that. Let's see if I want to go back and heard any of this other terminology. Hold on. Yep. Okay. So energy level, this is like the row or the period of the periodic table. You've probably thought of it as a shell, but I would like for you to start calling it energy levels. Now, a little note here, S and P orbitals hold valence electrons. Valence electrons are not found in d orbitals, generally speaking. Okay, valence electrons are not found in d orbitals. Let me talk about this too really quick. You always, when you remove an electron, you always remove it from the outermost shell or the highest energy level, okay? If iron is going to bond with somebody and become a cation, or like become maybe Fe+2 and lose 2 electrons, he's going to lose the 4s. Why? Because that 4 is the highest energy level. It's the outermost shell or ring. You always pull electrons from the outermost shell or ring. Okay, that's it.